Yes, we expect James Webb to make great discoveries. We expect that.
It has been 2 years since NASA's James Webb Telescope gave us a stunning first look at the depths of our universe. The $1 billion telescope is the largest and most powerful in space. It captured these images.
Most surprising is Mercury, the least explored of the rocky planets due to the difficulty of getting into orbit around a planet so close to the Sun. Mercury has long been a subject of fascination and mystery due to its extreme temperatures, high gravity, and proximity to the Sun, which posed major challenges for space missions. Different scientists tried repeatedly to peer into its confines but failed until NASA broke the jinx by sending the Mariner 10 spacecraft, which provided the first up-close images and data about the planet's surface and characteristics. In the years that followed, other explorations revealed new insights about Mercury. However, many were shocked when reports circulated that NASA had allegedly tried to hide a groundbreaking discovery made by the James Webb Space Telescope during one of its observations of the planet. But why would NASA hide such a secret from the public? What are its implications? Let's find out. Unveiling Mercury's mysteries. Launched in 1973, the Mariner 10 mission was the groundbreaking and trailblazing spacecraft that first embarked on a mission to visit Mercury, providing us with an unprecedented and never-before-seen close-up view of this enigmatic and mysterious planet. During its flybys, it managed to capture images of a landscape dotted with numerous craters and unusual ridges bearing a resemblance to our Moon. This mission unveiled and revealed Mercury's rugged, crater-filled exterior, a surprisingly strong and robust magnetic field, and a core that was larger than expected. These findings significantly challenged and questioned the assumptions scientists previously held about Mercury's composition. Then came Messenger, launched 31 years after Mariner 10. Messenger advanced our knowledge of Mercury to entirely new levels. Unlike Mariner 10, Messenger was specifically designed to orbit Mercury, allowing for a more detailed and comprehensive exploration of the planet. It captured an impressive total of 200,000 photos, uncovering parts of Mercury that had never been seen before. While these discoveries were made known to the public, the most recent, which was made by the James Webb Telescope, for strange reasons, was hidden from the public. But why? We're about to find out. One of the most fascinating and intriguing discoveries from Messenger was the high levels of calcium and magnesium found on Mercury's darker side. This unexpected finding raised questions about the processes that could lead to such concentrations. Additionally, Messenger found that Mercury's magnetic field was surprisingly strong in its northern regions, a trait that was not commonly observed in other planets. These revelations led scientists to a new understanding of Mercury's internal structure and formation process, which turned out to be quite different from what they initially thought. While on most planets, such as Earth, magnetic fields are created by the movement of liquid iron in the core, Mercury's unique and distinctive internal structure results in different magnetic characteristics. But that's not all. To make it more interesting, Messenger also revealed that the planet's terrain had craters and ridges, which is also different from what was earlier thought by scientists. During the day, temperatures can escalate to an astonishing 430 degrees Celsius (86 degrees Fahrenheit), which is indeed hot enough to cause lead to melt. Conversely, at night these temperatures plummet to an extreme low of minus 180 degrees Celsius (-292 degrees Fahrenheit). This dramatic fluctuation in temperature is attributed to Mercury's very thin exosphere, which barely has the capacity to moderate the temperature or retain heat effectively. To add to the trove of discoveries, data collected from the Messenger mission showed that Mercury's rotation pattern is very unusual compared to other planets in our solar system. While most planets rotate once on their axis in the same amount of time it takes them to orbit the Sun once, Mercury's rotation is much slower. Specifically, it takes Mercury 58.6 Earth days to complete one full rotation on its axis, known as a sidereal day. However, it only takes Mercury 88 Earth days to orbit the Sun once, known as a year. This means Mercury's day-night cycle is not one-to-one with its year, as is the case for most other planets. Instead, Mercury has a unique 3:2 spin-orbit resonance. This means that for every 3 rotations Mercury makes on its axis, it completes 2 full orbits around the Sun. As a result, a single solar day on Mercury, the time from one sunrise to the next, lasts an incredibly long 176 Earth days. This is twice as long as a full Mercurian year. The reason for this unusual rotation pattern has to do with Mercury's small size, oval-shaped orbit, and lack of a substantial moon. Without a large moon exerting strong tidal forces, Mercury's rotation is not locked to its orbit in the same way as the other terrestrial planets. Instead, the 3-to-2 spin-orbit resonance is the stable configuration for Mercury, given its physical properties. This extreme day-night cycle means one side of Mercury is in constant sunlight for 88 Earth days, while the opposite side is in perpetual darkness for the same duration. But you know what was the most shocking of all? It was when scientists in 2020 announced the discovery of water ice within some of Mercury's polar craters. For a planet that was the closest to the Sun, it was surprising that such a planet could hold the potential to support life, just like planet Mars. If you think this discovery was groundbreaking, wait till you hear the secret that NASA attempted to hide from the world. But before we go into that, there's more to know about this interesting planet, so sit tight as we layer by layer uncover more discoveries that were brought to light. Other interesting discoveries made in Mercury. Have you ever wondered what makes Mercury's orbit so unique? With an eccentricity of 0.21, Mercury's distance from the Sun varies wildly, ranging from 46 million to 70 million kilometers. That's a whopping difference of 24 million kilometers. But wait, there's more. Mercury takes a mere 87.969 Earth days to complete one orbit, making it the fastest-moving planet in the solar system. And if you thought that was impressive, now here's where things get really interesting. The varying distance between Mercury and the Sun causes tidal bulges on the planet's surface, raised by the Sun's gravitational pull. These bulges are a staggering 17 times stronger than the Moon on Earth, and with the 3:2 spin-orbit resonance, Mercury's rotation around its axis creates complex temperature fluctuations. But what does this mean for Mercury's surface temperature? Well, a single solar day on Mercury lasts exactly 2 Mercury years, or about 176 Earth days. That's a long time to wait for the Sun to rise again, and with temperatures fluctuating wildly, it's a wonder anything can survive on this scorching hot planet. Mercury's orbit is full of surprises. First, did you know that Mercury's orbit is tilted at a whopping 7 degrees compared to Earth's orbit? That's the largest tilt among all the planets. This means that Mercury's path around the Sun is quite unique, and its transits across the Sun's face are relatively rare, occurring only in May or November, and about every 7 years. With a tilt of just 0.027 degrees, Mercury's axis is almost perfectly upright, making it the planet with the smallest axial tilt. To put that into perspective, Jupiter's axial tilt is 3.1 degrees, which is significantly larger. This tiny tilt has some remarkable effects on Mercury's surface. For an observer at the poles, the Sun never rises more than 2.1 arc minutes above the horizon. That's incredibly low, and when you consider the Sun's angular size from Mercury ranges from 1.25 degrees to 2 degrees, it's clear that the Sun's movement appears quite unusual. In fact, at certain points on Mercury's surface, the Sun appears to rise, then set, and rise again, all within the same day. This occurs because Mercury's orbital velocity equals its rotational velocity around perihelion, causing the Sun's apparent motion to cease. It's like the Sun is dancing in the sky. If Mercury were in synchronous rotation, this effect would be even more dramatic. With a libration of 23.65 degrees in longitude, Mercury's unique orbit creates some fascinating phenomena. Let's explore them further. Imagine 2 points on Mercury's equator, 180 degrees apart, where the Sun appears to pass overhead not once, not twice, but 3 times in a row. This occurs around perihelion when Mercury is closest to the Sun and happens in alternate Mercurian years. The Sun's apparent motion reverses, and it seems to stand still in the sky for about 16 Earth days. This prolonged exposure makes these points the hottest on Mercury. But that's not all. The Sun's retrograde motion creates 2 other points on the equator, 90 degrees away from the first ones, where the Sun passes overhead only when Mercury is at aphelion, the farthest from the Sun. These points receive much less solar heat, making them cooler than the first ones. Mercury's approach to the Sun. Now let's talk about Mercury's close approach to Earth. On average, Mercury comes close to Earth every 116 Earth days, but this interval can vary due to its eccentric orbit. In fact, Mercury can come as close as 82.2 million kilometers to Earth, and that distance is slowly decreasing. But it won't be closer than 80 million kilometers until the year 28622. Mercury's retrograde motion, as seen from Earth, can last anywhere from 8 to 15 days on either side of its closest approach. This large range is due to Mercury's highly eccentric orbit. When it came to mapping Mercury's surface, scientists faced a challenge. The zero longitude point was initially set at one of the two hottest points, but when Mariner 10 first visited, that area was in darkness, so they chose a small crater called Hinel, which is now the reference point for measuring longitude. Now let's talk about Mercury's spin-orbit resonance. For a long time, scientists thought Mercury was tidally locked with the Sun, rotating once for each orbit. But radar observations in 1965 revealed a surprising 3:2 spin-orbit resonance. Mercury rotates 3 times for every 2 revolutions around the Sun. This resonance is stable due to Mercury's eccentric orbit at perihelion, when the solar tide is strongest. The Sun appears nearly stationary in Mercury's sky. This unique resonance makes Mercury's rotation and orbit deeply connected. The 3:2 spin-orbit resonance means that after one orbit, Mercury has rotated 1.5 times, and after 2 complete orbits, the same hemisphere is again illuminated. This resonance has a profound impact on Mercury's surface temperature and geological activity. Mercury's 3:2 resonant tidal locking is stabilized by the varying tidal force along its eccentric orbit. This force acts on a permanent dipole component of Mercury's mass distribution, causing the planet's axis of least inertia to point roughly at the Sun when passing through perihelion. In a circular orbit, only a 1:1 resonance is stabilized, like the Earth-Moon system. But Mercury's eccentric orbit allows for more complex resonances like the 3:2 spin-orbit resonance. Astronomers initially thought Mercury was synchronously locked because it always showed the same face when best placed for observation. However, this was due to a coincidence. Mercury's rotation period is almost exactly half of its orbital period with respect to Earth. Now let's talk about Mercury's day lengths. A solar day on Mercury lasts about 176 Earth days, while a sidereal day, the period of rotation, lasts about 58.7 Earth days. This means that a day on Mercury is actually 2 of its years. The 3:2 spin-orbit resonance has a profound impact on Mercury's surface temperature and geological activity. It's a remarkable example of how celestial mechanics can shape the behavior of a planet. Have you ever wondered how Mercury's rotation is connected to its orbit? It's a fascinating story. Mercury's eccentric orbit creates a varying tidal force that acts on the planet's mass distribution, stabilizing a 3:2 resonant tidal locking. This means that Mercury's rotation is linked to its orbit in a way that's different from the Earth-Moon system. In a circular orbit, the tidal force would align the planet's axis of least inertia to always point at the center. But Mercury's eccentric orbit creates a maximum tidal force at perihelion, stabilizing the 3:2 resonance. This ensures that Mercury's axis of least inertia points roughly at the Sun when it passes through perihelion. Astronomers initially thought Mercury was synchronously locked because it always showed the same face when observed, but this was just a coincidence. Mercury's rotation period is almost exactly half of its CTIC period with respect to Earth. So, how long is a day on Mercury? A solar day lasts about 176 Earth days, while a sidereal day, the period of rotation, lasts about 58.7 Earth days. That's a pretty slow rotation. The 3:2 spin-orbit resonance has a profound impact on Mercury's surface temperature and geological activity, making it a unique and fascinating planet to study. What has the James Webb Space Telescope discovered on Mercury? The James Webb Telescope is a game-changer in modern astronomy. This incredible tool has made a jaw-dropping discovery on Mercury, the smallest and innermost planet in our solar system, and trust me, it's got everyone in the scientific community buzzing with excitement. Mercury, with its sizzling temperatures and rugged surface, has always been a mysterious and fascinating world, but its close proximity to the Sun has made it a challenging subject to study in detail. That was until the James Webb Telescope came along. With its cutting-edge infrared imaging capabilities, this technological marvel has finally allowed us to peek behind the curtain and uncover some of Mercury's secrets. So, what did the telescope discover in one of its observations of the planet? The James Webb Telescope uncovered previously unknown volcanic features that challenge our current understanding of the planet's geological history. These vast, smooth areas, known as volcanic plains, reveal a dynamic and active past filled with volcanic eruptions that shaped the planet's surface. The James Webb Telescope's infrared sensors have allowed scientists to map the distribution of potassium and sodium across the plains, providing a detailed understanding of their formation. These elements, indicative of volcanic activity, suggest that Mercury's interior was once hotter and more active than previously thought. This discovery has significant implications for our understanding of Mercury's evolution. It suggests that the planet's interior was fueled by the decay of radioactive elements, contributing to the formation of its distinctive surface features. The James Webb Telescope's observations provide valuable insights into the early history of Mercury, shedding light on the mysteries of our cosmic neighborhood. This knowledge is crucial for understanding the evolution of other terrestrial planets in our solar system, including Earth. As we continue to explore the volcanic plains, we may uncover even more secrets about Mercury's hidden past and the formation of our solar system. The discovery of volcanic plains on Mercury challenges previous theories that suggested the planet was dormant. But this is not the first time humans have tried to understand the strange planet. Apart from NASA, other humans have attempted to explore the planet. Let's take a look at the numerous times throughout history that humans explored or tried to learn more about Mercury. Observation history of Mercury. The earliest known recorded observations of Mercury are from the Upend tablets. These observations were most likely made by an Assyrian astronomer around the 14th century BC. Babylonian records of Mercury date back to the 1st millennium BC. The Babylonians called the planet Nebo. This was the name of the messenger to the gods in their mythology. The Egyptian astronomer Tmy wrote about the possibility of planetary transits across the face of the Sun. In his work, Planetary Hypotheses, he suggested that no transits had been observed, either because planets such as Mercury were too small to see or because transits were too infrequent. Ibn al-Shaddad's model for the appearances of Mercury shows the multiplication of epicycles using the Tusi couple, thus eliminating the eccentric models. In ancient China, Mercury was known as the R star. It was associated with the direction north and the phase of water in the 5 phases system of metaphysics. Chinese, Korean, and Japanese cultures refer to the planet literally as the water star, based on the 5 elements. Hindu mythology used the name Buddha for Mercury, and this god was thought to preside over Wednesday. The god Odin, or Woden, of Germanic paganism was associated with the planet Mercury and Wednesday. The Maya may have represented Mercury as an owl, or possibly 4 owls, 2 for the morning aspect and 2 for the evening, that served as a messenger to the underworld. In the 12th century, Ibn Bajjah observed 2 planets as black spots on the face of the Sun, which was later suggested as the transit of Mercury by the astronomer Alan Shirazi in the 13th century. Most such medieval reports of transits were later taken as observations of sunspots. In India, the Kerala school astronomer Nilkantha Somyaji, in the 15th century, developed a partially heliocentric planetary model in which Mercury orbits the Sun, which in turn orbits Earth, similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. The first telescopic observations of Mercury were made by Thomas Harriot and Galileo from 1610. In 1612, Simon Marius observed that the brightness of Mercury varied with the planet's orbital position and concluded it had phases in the same way as Venus and the Moon. In 1631, Pierre Gassendi made the first telescopic observations of the transit of a planet across the Sun when he saw a transit of Mercury predicted by Johannes Kepler. In 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. The observation demonstrated conclusively that Mercury orbited the Sun. A rare event in astronomy is the passage of one planet in front of another, known as an occultation. As seen from Earth, Mercury and Venus occult each other every few centuries, and the event of May 28, 1737, is the only one historically observed, having been seen by John Bevis at the Royal Greenwich Observatory. The difficulties faced when scientists tried to observe Mercury meant that it was far less studied than the other planets. In 1800, Johann Schroer made observations of surface features, claiming to have observed high mountains. Friedrich Bessel used Schroer's drawings to erroneously estimate the rotation period as 24 hours and an axial tilt of 70 degrees. In the 1880s, Giovanni Schiaparelli mapped the planet more accurately and suggested that Mercury's rotational period was 88 days, the same as its orbital period, due to tidal locking. The effort to map the surface of Mercury was continued by Eugenios Antoniadi, who published a book in 1934 that included both maps and his own observations. In June 1962, Soviet scientists at the Institute of Radio Engineering and Electronics of the USSR Academy of Sciences, led by Vladimir Kotelnikov, became the first to bounce a radar signal off Mercury and receive it, starting radar observations of the planet. 3 years later, radar observations by Americans Gordon H. Pettengill and Rolf B. Dice, using the 300-meter wide or 330-yard Arecibo radio telescope in Puerto Rico, showed conclusively that the planet's rotational period was about 59 days. The theory that Mercury's rotation was synchronous had become widely held, and it was a surprise to astronomers when these radio observations were announced. If Mercury were tidally locked, its dark face would be extremely cold, but measurements of radio emissions revealed that it was much hotter than expected. Astronomers were reluctant to drop the synchronous rotation theory and proposed alternative mechanisms, such as powerful heat-distributing winds, to explain the observations. In 1965, Italian astronomer Giuseppe Colombo noted that the rotation value was about 2/3 of Mercury's orbital period and proposed that the planet's orbital and rotational periods were locked into a 3:2 resonance. Data from Mariner 10 subsequently confirmed this view. This means that Schiaparelli's and Antoniadi's maps were not wrong. Instead, the astronomers saw the same features during every second orbit, recorded them, but disregarded those seen in the meantime when Mercury's other face was toward the Sun because the orbital geometry meant that these observations were made under poor viewing conditions. Ground-based optical observations did not shed much further light on Mercury, but radio astronomers, using interferometry at microwave wavelengths, a technique that enables the removal of solar radiation, were able to discern physical and chemical characteristics of the subsurface layers to a depth of several meters. Not until the first space probe flew past Mercury did many of its most fundamental morphological properties become known. Moreover, technological advances have led to improved ground-based observations. In 2000, high-resolution Lucky imaging observations were conducted by the Mount Wilson Observatory's 1.5-meter Hale telescope. They provided the first views that resolved surface features on the parts of Mercury that were not imaged in the Mariner 10 mission. In 1965, Italian astronomer Giuseppe Colombo made a groundbreaking observation. He noticed that Mercury's rotation period was about 2/3 of its orbital period and proposed a 3:2 resonance between the two. This meant that Schiaparelli's map wasn't incorrect but rather that they saw the same features every second orbit and disregarded the rest due to poor viewing conditions. Mariner 10's data later confirmed Colombo's theory, revolutionizing our understanding of Mercury's rotation. But despite this breakthrough, ground-based optical observations didn't reveal much more about the planet. That was until radio astronomers used a new technology known as interferometry to study Mercury's subsurface layers, uncovering physical and chemical characteristics to a depth of several meters. It wasn't until the first space probe flew by Mercury that many of its fundamental properties were discovered. With technological advancements, ground-based observations improved too. In 2000, the Mount Wilson Observatory captured high-resolution images of Mercury's surface, revealing features that Mariner 10 had missed. Today, most of Mercury has been mapped by the Arecibo radar telescope, with an impressive 5 km resolution. Polar deposits and shadowed craters, which might be water ice, have even been discovered. Despite everything scientists know about Mercury right now, the mysterious planet still holds many intriguing secrets that are waiting to be uncovered. That's why several missions are planned to explore the planet in the future. As we approach 2025, the European Space Agency, ESA, and Japan Aerospace Exploration Agency, JAXA, joint mission, Bepi-Colombo, is closing in on Mercury, aiming to uncover the planet's magnetic field, surface, and interior secrets. Building on the discoveries of NASA's MESSENGER, Mercury remains a subject of fascination, with its extreme temperatures and proximity to the Sun posing unique challenges for space exploration. However, the quest to understand this enigmatic world continues, driven by scientific curiosity and the potential for groundbreaking discoveries. NASA is also considering future missions to investigate Mercury's exosphere, magnetic field, and polar ice deposits, aiming to expand our understanding of the planet's evolution and its role in the solar system's history. The global interest in Mercury exploration highlights the shared commitment to understanding our solar system. Other nations and private companies are joining the Mercury exploration efforts, potentially leading to innovative partnerships and advancements in space technology. These endeavors are not just about reaching Mercury, but also about fostering international cooperation in the pursuit of knowledge. Bepi Colombo's arrival in 2025 will mark a new era in Mercury exploration, providing unprecedented insights into the planet's magnetic field, surface, and interior. NASA's future missions will further expand our understanding of Mercury's exosphere, magnetic field, and polar ice deposits, shedding light on the planet's evolution and its role in the solar system's history. The future of Mercury exploration is bright, with innovative partnerships and advancements in space technology on the horizon. As we continue to explore this enigmatic planet, we may uncover secrets that challenge our current understanding of the solar system and inspire new generations of scientists and engineers. The quest to understand Mercury is a testament to human curiosity and the pursuit of knowledge, driving us to continue exploring the vast expanse of our solar system. While ESA and JAXA are making significant progress with the Bepi Colombo mission, NASA is also looking toward the future with plans for Mercury exploration. Although specific missions have yet to be announced, the agency is actively exploring concepts that will build on the groundbreaking findings of the Messenger and Mariner 10 missions. These future missions could delve into the uncharted territories of Mercury's thin atmosphere, known as the exosphere, its magnetic field, and the ice deposits in its shadowed craters. NASA's interest in Mercury extends beyond mere revisitation. It seeks to answer profound questions about the planet's formation and its role in the solar system. By building upon the foundations laid by past missions, NASA aims to uncover more about this enigmatic rocky world and contribute significantly to our understanding of the cosmos. NASA is not the only one with plans to explore Mercury. The China National Space Administration, CNSA, and Russia's Roscosmos have expressed ambitions to venture into the unknown territories of this enigmatic planet. Although concrete plans are still in development, their involvement could lead to innovative missions in the coming decades. Private space companies are also recognizing the vast potential of Mercury exploration, acknowledging the scientific and technological advancements that could arise from such endeavors. As these entities develop their capabilities, they may offer groundbreaking solutions and partnerships for reaching and studying Mercury. Exploring Mercury, the smallest and innermost planet, presents numerous challenges due to its extreme proximity to the Sun. However, these challenges have driven innovations in materials science, spacecraft design, propulsion systems, and power generation. To navigate Mercury's extreme temperatures, spacecraft employ multi-layer insulation blankets, heat-resistant materials, and reflective coatings. Communication delays are addressed through autonomous systems, while durability is ensured by robust electronics, durable materials, and redundant systems. Advancements in propulsion systems, such as solar electric propulsion, SEP, and power generation including radioisotope thermoelectric generators, RTGs, have made deep space missions more practical. Robotic missions play a crucial role in paving the way for future human exploration. Unmanned spacecraft provide valuable data, test new technologies, and operate in hazardous conditions without risking human life. These missions have been instrumental in understanding Mercury's environment and laying the groundwork for future exploration. Robotic missions contribute significantly to future human exploration, including identifying potential resources, testing technology for processing materials, and experimenting with life support systems. The knowledge gained from these missions will inform strategies for future human exploration of Mercury and the broader solar system. What do you think of the new discoveries on Mercury by the James Webb Telescope? Let us know your thoughts in the comments section. If you enjoyed this video, please like and subscribe to our channel to stay updated. Thank you for watching, and we'll catch you in the next one.